Hello folks, this is tutorial number 32 from the dynamic scenario playlist in the 3D Experiences platform. What I want to do is a relatively simple problem, and that is to obtain the period of oscillation of a nonlinear pendulum and compare it with what the 3D Experience predicts. That reference that you see at the bottom is a really good reference for a general nonlinear pendulum. But anyway, things that we're doing are a lot simpler than what these people are talking about. Now, what do we mean by nonlinear pendulum? That is when you release the bob of the pendulum from different heights. So, for example, if you look at the problem that we're going to do, the top joint is going to be a revolute joint between the base and the rod, massless rod, and the bottom joint is a rigid joint between a big blob of mass and the massless rod. Now, if you look at this thing from the front, and the length of the rod is L, and you tilt the bob by angle theta naught and just let it go, due to the gravity, assuming there are no frictional losses, it's going to oscillate forever about that vertical position. And the period of that oscillation in the elementary vibration course, you were taught that is given in terms of the length of the pendulum and the gravity constant. Now, for example, it has nothing to do with the size of the mass, but let's say that the mass, the rod of the rod has a mass of very small mass, 0.01 kilogram, approximately zero, as compared to the mass of the bob, which is 10 kilogram, and the length of the rod is 0.25, and gravity constant is the standard 9.8 meter per second squared. And we release this bob from a 5-degree angle. This is considered to be a linear analysis, and the formula that you were given in the physics class or elementary vibrations class is the period of oscillation is 2 pi root of L over G, which happens to be in this case 1.0035. And this is irrespective of whether you release it from 1 degree, 2 degree, 3 degree, 4, all the way to approximately 8 or 9 degrees. That is almost the correct answer. But if the bob is deflected a lot, is raised a lot, and released from that height, the period of oscillation will actually change, and this is what we are trying to do here. So this is the formula for linear period. This is the formula for nonlinear. Notice that in this expression, there's the period when released from a height from an angle of theta degrees, and it's equal to T naught plus some other stuff. In fact, this is an approximation because this is an infinite series. It goes on and on and on, and it can also be described as an elliptic integral, but that's not what we're doing. We're using this formula as our reference. Okay. So what I'm going to do is I'm going to model this thing and release it from 5 degree, and then 45 degree and 90 degree. And this formula predicts that the period of oscillation for angles larger than 7-8 degrees is going to be depending on the actual, heavily depending on the actual angle. And for example, at 90 degrees, it's going to oscillate at 1.17 almost 1.8 seconds, as opposed to this is which is almost 1 second, almost 1 second. So in fact, if you plot this thing, this is the linear analysis. 5 degree release angle is going to give you a period of 1.0035 second. 45 is going to give you 1.05, so there's a substantial difference here. You can see that. And at 90 degrees, it's going to be 1.1759, etc. So these are the numbers that we're going to compare our analysis with. Okay, so let's go ahead here. And I'm going to start with assembly design, because we're going to create a mechanism. There it is. Let's insert our first piece, which is going to be the wall, if you want. So it's going to be a 3D part, and I'm going to call this thing the pivot point. How about the pivot base? Okay, so properties, I'll call it pivot base. Pivot base. Pivot base. All right, let's go make it. Very simple. It's just a cylinder basically. So on that vertical plane, I will sketch a circle, something like that. Exit and pad it. Okay, I'll pad it in the other way, in the other direction, right there. Okay, and then sure, I'm going to change the color here. Properties, graphics, change the color. I don't know what I did. Maybe green or something. Okay, and we go all the way to the top. Insert our massless rod. So right click, insert, 3D part. I'm going to call it rod. Properties, rod, rod, massless rod, of course. Will be assigned very small mass. Double click on this, and on a convenient plane, for example, on this plane, I will sketch. Why don't I do the following? I will do I'll do one of these elongated hole. I put the cursor there. Right there, right there, and why don't I make this length 0.25? 0.25 meter. So there is your rod. Exit. Let's pad it. Let me make this thing a little bit smaller, maybe 0.01. These sizes don't matter except for the L. L, of course, does come into the picture. So this, from the center of this to the center of that is 0.25. Okay, I want to change the color too. I'll change that thing to orange or yellow. Okay, good, good. Now we're going to insert the bob. So insert 3D part in there. Right click properties, bob, or the mass if you want, and bob, pendulum bob, and the graphics if you want to change the color, change it to orange. Let me say okay. We will of course make it. Haven't done it yet. So on that plane, I will sketch. Okay, let me go to this part first. On that plane, I will sketch a circle like that. The actual size of this thing doesn't matter. The mass of it will matter. So I'll just leave it the way it is. How about that? I'll just leave it the way it is. Maybe a little bit bigger. Good. Now let's make sure that this is concentric with that, because I want to make later on. It really doesn't matter. I just want it to be concentric. Let me see. We'll go here. Concentric right there. Okay. Very good. Exit. And then we pad it. Pad it, but in the other direction. Let me see. Is that what I wanted? Yep. Okay. So that's fine. There we are. Now, why don't I create a point while I'm at it? Create a point at the center of this, center of the circle, because later on I want to put a probe there. Very good. So all the way to the top. Save everything. Now notice that I don't have any constraints. They look good because they were made to look like that. Okay. So here's what I'm going to do. Let's create our joints. It will be helpful if I actually move these things. So let me go Go ahead and do that. Use the manipulate. So let me translate stuff. Translate it in the, I don't know, in the X direction. Oops, in X direction, like that, and like that. Good. Okay. So first thing we're going to do is to create a to create a fixed part. So it's going to be fix. I'm going to fix the pivot base. That's fixed. There you can see that. Okay. And then I'm going to create a revolute between this rod and that base. So revolute. There's this revolute. There are different ways of doing it. I will use this one. Axis and axis, plane and plane. Really doesn't matter. Actually, let me try it again. The first thing that you do is going to get moved. Of course, this is fixed. I realize that, but I don't like it when things that are fixed are moving. There we are. And for plane and plane, for example, we can do this plane and that plane there. And this last one, I don't need it. I'm going to just delete it. Say OK. Now I'm going to create a rigid joint between this and this. So let me see now. First of all, let me use the snap to put it there. Snap. Snap this end with that end. Okay, good. And then we make a rigid joint. There are different ways of doing it. I will use this last one. Makes no difference. So that rod, massless rod, and this bob. Okay, good. Now, because I want to be able to change this vertical angle, I'm going to create a constraint here. It's called engineering connection, and click on this three dots and make an angle constraint. See that angle constraint between the vertical plane of you can do the vertical plane of the base of the pivot at the wall and this angle, for example, or this face, for example. Really, yeah. Let me try that. So angle between the vertical plane, this vertical plane, XZ plane, and this plane over here, and create a new one. Right now it's 50, I don't know, 53 degrees. I'll make it 5 degrees. 5 degrees. Say okay. No, and update. This will actually shift like that. Okay, good. We're done. Now we're pretty much done here. So let's go ahead to the mechanical systems design. First, we assign the masses. So scroll all the way down here. Oh, you have to select this mechanical systems tab, mechanical systems design tab, and scroll all the way down. Here is the weight definition. This is really mass, not weight. So we select first of all the pivot base. And since this is not moving, its mass is not important, but we do have to specify something. So I'm going to click on this box here and notice the properties of a steel are given. But what I can do is I can put the cursor here. This is terrible. I'm expecting a little window open up here. Oh, it comes and goes. I don't know why it's so finicky. Okay. Ah, missed it. You know what? Let me do the following. Let me move this thing here and click on it. Now, oh, there. 0.01. I don't know why it behaves like that. Done. So notice that 0.01 is put in there. You close that. Then we're going to do the massless rod. So you click on that. this was the base. It didn't matter, but I changed it. Actually, I could have left it the way it is, but that's okay. So click on that. Again, click on this box, properties of steel, put in there. And you, honestly, okay, there. Also 0.01. I really didn't mean to change that wall or base pivot base. I could have left it the way it was because that wall is not moving anyway, but I changed this 0.01. That's the mass of the rod. And finally, you click on the bob, or close that, click on the bob, apply this hyperlink, click on this checkbox, and now we're going to put 10 kilogram there, right there, 10 kilogram. 100 times bigger than that rod. Okay, everything is blue here, which is a good sign. Close that. Now, remember that vertical angle was 5 degrees. Now, we're pretty much done here. We're going to create a mechanism. There is the mechanism representation. Say OK. And then click on that. Notice that it gives you a fixed part, a revolute, a rigid, and that, remember that the thing that I applied 5 degrees here? This really is not important. I can uncheck it because all I wanted to do position that, and then we say OK. Good. We are done. So we're going to go to mechanical systems experience. Say OK. Say OK. First of all, make sure that the gravity is applied. Gravity is right here. Gravity. Click. Minus 9.81 meter per second squared downward. Very good. Now let's do a sensor. Here is a position sensor, position and acceleration sensor. Basically, you select this point because later on I want to plot the position of this. I say OK. And that's pretty much it. So we go here, dynamic scenario, gravity excitation we add, probe we add, and we're going to do that over 5-second interval. I'll use the DASSL, which stands for Differential Algebraic System Solution Solver. Differential Algebraic Solution Solver. We say OK. And that's pretty much it. So we're going to go put the cursor there, right click and run it. Let's see what happens. This is going to go 5 seconds. There are no frictional losses. So if we do this thing for 100 seconds, it's going to go almost 100 times. Now, if you click on this, if you click on that, it allows you to plot some stuff. So deselect everything. Let me plot the Y position, of that probe that I put in there, for that point. And if you click on it, it goes like that. So one oscillation is this much, and this better be approximately 1 second, and it is. Look, 1 second. In fact, if you go to the table, at time 0, that was the Y position. If you go to the next time that the vertex is this, it'll give you the time. So scroll down. What was the number? 0.022. So let's scroll down. There we are. 0.022, 0.99, which matches almost that. Okay, very good. Now what we're going to do is we're going to say, okay, let me close that. We're going to say, okay, I want this angle to be, for example, 90 degrees. So let's go ahead and do that. 90 degrees. So what we're going to do, we're going to go to this restraints that I put in there. See that? See this? This is the user-defined restraint for angle that I define. You double click on this, and you make this thing a 90. That's okay. And update, you see what happens. There we are. So this is, we look at the front, it looks like that. Okay, you could have done the 45, but I did the 90. I'm not going to do the 45. That's pretty much it. So you go back to the scenario. Make sure you're there, and We're doing it over 5 seconds. So run it. This is going to be less than 5 oscillation though, because the 1, 2, 3, 4. Yeah, good. So let's look at the plot now. Click on this. Deselect all. Look at the Y position and plot it. No, this is not sine anymore. If the angle is large, this oscillation is not sinusoidal anymore. And also, if you want to know what is the period, you can look at it. The period goes up to this point, right? Which is 1 point something. But if you want to know exactly where it is, you go to the table, 0.25. Next time it goes to the height of 0.25. It's negative. Scroll down, 0.25. It's kind of 1.15-ish, 1.15-ish. So you go to the formula here, 1.15. Actually, it's really more than that. If we go back here, 0.25 ends around, yeah, pretty much around here, 1.25. Or you can argue that actually it happens before that. Yeah. So pretty much here, because this is kind of a flat curve. Let's try it again. What happened? Did it freeze? Let me run this thing again. Oh, there we are. Okay, that's fine. Deselect everything. Y vertex. You look at it like that. So you know these are all pretty much the same thing. So we want somewhere around here, which is very close to your 1.17. Okay, because those numbers that are looking at one, you know, I told you 1.25. You're probably looking at these positions. Anyway, if you are not sure, let's go ahead and do the angle 45 degrees. I was not going to do that, but I'll do it. Let's make this thing 100. Let's make this thing 135. Okay, and update. Oh, no, 135, 145. Sorry. Let's go back here. Oh, this angle. Let's go to 45. Yep. Okay, and then run it. Put the cursor here. Try to run it. Now notice that it didn't run. That's because you're not in the right spot. You're not in the mechanical system experience. You're not there. So double click on this, or maybe hit the escape and then double click on it. Right now, see, you are in the right spot, right application, and run it. And then plot it. Okay, deselect everything. Y vertex. And you see, if the angle goes, that initial drop angle goes to, gets smaller and smaller, this becomes more close to sinusoid. And here it's going to be around 1 point something. So let's check it out. 0.177. When does it go to 0.177? 0.177. Yeah, around here maybe 0.9. And let's see that. 0.177. Wait a minute. 0.177. 1.04. 1.04. See that? 1.04. And if you go here, you get 1.04. All right, folks.